We've kind of talked about this before when we were talking about polynomial equations, but two properties of roots of polynomial equations that we really need to touch on, make sure that we know, are these below. First off, if a polynomial equation is of degree n, then counting multiple roots separately, the equation will have exactly n roots. So in this case, like if it is a cubic, so as the highest degree is 3, then that means it will have 3 roots. These roots may be real or imaginary though. The second one that we need to know that if a plus bi is a root of a polynomial equation with real coefficients, then the imaginary number a minus bi is also a root. You can think of this as if an imaginary root, if it exists, it's going to occur along with its conjugate. So let's practice these properties by fully solving the polynomial equation below. First of all, we want to point out how many roots it's going to have. If you notice in this case, since the degree is 4, then this means it's going to have 4 zeros. Again, these might be real or they might be complex, or imaginary, I mean. We're going to start by listing out all possible rational roots. In this case, remember that's going to be the factors of the constant term over the factors of the leading coefficient. And since our constant term is 13, that'll just be plus or minus 13 and 1, and the leading coefficient is 1, so our only possible rational roots here will be plus or minus 13, or plus or minus using 1. Since it's not going to be possible for us to actually do factoring here, we're going to use the synthetic division to test possible rational zeros. Remember, we can also use the graph here to pick which ones we think would be most likely. We're just going to try some guess and check here though on this one. So, first of all, I'm going to start with positive 1. If we set up our synthetic division and go ahead and bring down the 1 and do our adding and multiplication, we will find here that we're going to get a remainder here out of 0, which in this case means that positive 1 is a 0 of this polynomial. And so that means we can go ahead and rewrite this polynomial as x minus 1 times the coefficients, which would be left over to be x cubed, minus 5x squared plus 17x minus 13 equal to 0. And so we now have one factor. We need to go ahead and continue and break down that cubic then to find the others. So now that we have found that that polynomial can be rewritten in that factor form, we're going to go ahead and work with that cubic there, the x cubed minus 5x squared plus 17x minus 13. Again, we're going to use the possible rational root property to help us do that. In this case, again, our constant term is negative 13. The leading coefficient here is 1. And so if we take all those factors and find the possible list, we get, again, plus or minus 13 plus or minus 1. And so we're going to do that. Since we can rewrite this again, I'm just going to go ahead and bring that down. Since we already know that x minus 1 is a factor, we're going to go ahead and try a different possible root in this case. Let's just go ahead and use 1 and try that guy. If we do our synthetic division here, and by add and multiply, screw up there. In this case, we're going to get out a negative 36, which means that negative 1 is not going to work. But if we try positive 1, again, we're going to get out a remainder of 0. So that means that we're going to have 2 zeros at 1. So that means that we're going to get x minus 1 as 2 factors. And so we can rewrite this as x minus 1 times x minus 1, and then rewrite our quadratic there of x squared minus 4x plus 13. It's perfectly okay for some zeros to repeat. Just remember that means it has a multiplicity. A different multiplicity. So now we have the factored form. We've changed that quartic to the x minus 1 times x minus 1 times our quadratic. We can go ahead and use the quadratic formula to solve our quadratic here because we cannot factor it. And so if we let a be 1, b be negative 4, and c be 13, we'll go ahead and set up our quadratic formula here of positive 4 plus or minus the square root of negative 4 squared minus 4 times that a times c all over that 2a. If we reduce our square root, we're going to get 16 minus 52, which if we go ahead and subtract, gives us a negative 36, which is going to come out as 4 plus or minus 6i all over 2, which we can divide everything by 2, giving us 2 plus or minus 3i. Notice in this case, since we have an I in both these zeros, these are going to be imaginary roots. And so our 4 total roots here were 1, 1, and then 2 plus 3i and 2 minus 3i, giving us exactly 4 roots. Also remember that if an imaginary root appears, it's going to have to appear with its conjugate, So since we had 2 plus 3i, we also got 2 minus 3i. One of the key components of all of algebra is what we call the fundamental theorem of algebra. This says that if f of x is a polynomial of degree n, where that degree is greater than or equal to 1, then the equation of f of x equal to 0 has at least one complex root. So this is saying that if we have a polynomial of at least degree 1, then it's going to have at least one root. Remember, in this case, that root can be real, it can be imaginary, because remember, complex numbers consist of both the real and imaginary numbers. This leads us to the linear factorization theorem that says if we have a polynomial, I'm not going to read that out, but where n is greater than or 1, and then our a not, so our leading coefficient is not 0, then that polynomial can be written as a sub n times x minus c1 times x minus c2 all the way up till x minus cn, where the c's are complex numbers, possibly real but not necessarily distinct, so they can repeat. In other words, an nth degree polynomial can be expressed as the product of a non-zero constant, the a, and then n linear factors, where each linear factor has a leading coefficient of 1. So any polynomial can be written as a set of factors, and then it might have a coefficient of not 1 out in front. We're going to use this to help us create polynomials given certain information. For example, if we wanted to find a third degree polynomial with real coefficients that has -3 and I as zeros, but then we also want the stipulations to be that f of 1 is equal to 8. In this case, we can use that factor linearization theorem to help us here. And we're always going to start with the zeros. So if we have zeros at -3 and I, that means that if x is equal to -3, well, if that's our 0, then that means our first factor of the polynomial must be x plus 3. Same thing, that if we have a 0 at I, and I subtract over that I, then that gives us the factor x minus I as another factor for this polynomial. But remember, we also talked about that. If a complex 0 appears, then its conjugate also has to appear, so that means x minus I is also going to appear. I'm going to rewrite that. So we're going to get x minus I, but if I move that over, it's going to be an x plus I. So now we have 3 factors, which if this needs to be a third degree polynomial, then it makes sense that it's going to have 3 factors. So we can put all those factors together to go ahead and create our polynomial. So I'm going to write f of x as that a, we don't know what that constant is, but it's going to include the x plus 3, the x minus I, and the x plus I, which we can go ahead and multiply all our factors together. And so I'm going to start by multiplying the x minus I and x plus I together, which is going to be like our difference of squares, but working backwards. So that's going to be as x squared minus I squared. But remember, I squared is the same thing as -1, so that's really going to be minus a negative, so we'll get x squared plus 1. And then I'm just going to FOIL our 2 binomials together, giving us a times x cubed plus 3x squared plus x plus 3. And so we can use this to help us find the a value, since we still need that. Remember, our last thing that we really needed to know was that f of 1 is equal to 8. Well, we can think of this as x is 1, then y must be 8. And so I'm going to plug in the 8 for the f of x, and then 1 for all the x's. And then we can go ahead and solve this, and solve for a. So we're going to get that 1 plus 3 plus 1 plus 3, which is 8. If I divide by 8, that means a is equal to 1. So our third degree polynomial function that has all this criteria is just going to be 1 times our cubic that we found before, x cubed plus 3x squared plus x plus 3. One other thing that we sometimes need to know about zeros are the signs of the zeros, either if they're going to be positive, real, or in this case negative. And so we have this lovely property here called Descartes Rule of Signs that will help us find the total number of positive or negative real zeros. So for any polynomial f of x, we know that the number of positive real zeros of that polynomial is either the same as the number of sign changes that's in the polynomial, or less than the number of sign changes in the polynomial by a positive even integer. If a polynomial has only one variation in sign, then that polynomial is going to have exactly one positive real zero. So when by sign changes, we're talking about changing from a positive to a negative in between terms. Same thing with negative signs. the number of negative real zeros is either the same as the number of sign changes in f of negative x, so we have to evaluate first, or less than the number of sign changes in f of negative x by a positive even integer. Again, if f of negative x only has one variation in sign, then that polynomial is going to have exactly one negative real zero. So let's try this out. Let's consider this polynomial. And we want to determine the number of possible signs, or number of positive and negative real zeros. Let's start with the positive. So remember, for a positive, it's all going to be based on the sign changes in the original polynomial. And so if we look at the polynomial, we have 4 variations in signs. So that means here that by Descartes' rule, that the number of positive real zeros must be the same as the degree or 2 less. So in this case, 4, 2, or 0, because it always has to go down by a positive even integer. So in this case, we have 4, 2, or 0 possible real zeros. For the negative then, what we need to do first is find f of negative x. So we're going to just plug in negative x for all the x's here. And then we're going to evaluate. Notice the negative x to the 4th, since it's an even root, is going to make that positive. I'm not finished writing that out, so that's going to make that positive. But since if we have that negative x cubed there, okay, that's going to be a negative x cubed, but then we have that negative out in front of that 14, so it's like another negative times that negative x cubed, making it a positive. If we square, we're going to get a positive there. Again, it's a negative 154 times the negative x, making it a positive as well. And then we also have that positive 120. So if we look here, we have no sign changes, which means that we are going to have no negative real zeros for this function. And so based on that right there, if we have no negative real zeros, then that means we must have 4 positive real zeros, because since this is a degree 4 polynomial, it must have 4 zeros. So that's how we're going to use Descartes' Rule of Signs. All these properties and theorems are here to help us with finding and solving polynomial equations, and also with the graphs. Please pause here and go back and look at any examples if you need to.